Okay, I'm going to talk a little bit about linear regression, and I'm going to be using Excel. I have a video up for doing it in StatCrunch. I just am a little more comfortable with doing a lecture, so to speak, in Excel. So here I have a set of data, and this data could simply be representing the number of weeks a person's in the diet and the total weight loss that they've had. Now I could have made these negative, but for purpose of this example, just remember that 1.5 means they've lost a total of 1.5 pounds. Here they kind of slip back a little bit, 1.3, and at the end of the 10 weeks they've lost a grand total of 8 pounds. So maybe not that successful on the diet, but you kind of picture what's happening here. So first thing you should do when presented with a set of data and being told to fit a regression or do linear regression on it is to actually see what it looks like when it's plotted in a scatter plot. And StatCrunch will do this. Again, I just kind of like it in Excel. So I see that's fairly linear. To make a judgment of how linear, I'm going to calculate correlation. And I'm going to use the correl command. And this correlation should be fairly high, so 0.96. And bear in mind, if you're on a diet, the number of weeks that you're on should kind of give you an indication of what the pounds that you lost is, at least if you're being fair or actually following the diet. So pretty high linear correlation. If I want to actually do regression in Excel, you click the chart. There's different ways of doing it. I'm going to hit this plus. I'm going to go down and click on trend line. I'm not going to select that box. I'm just going to click on trend line. Let's try it again. Click on the arrow by trend line. More options. And over here on the, try that again. It's fighting me. More options. Over here you see different options for polynomials, logarithmic, exponential. Like if I wanted to fit a polynomial to it, it'd be that. I don't really want to do that, or go back to linear. I do want to click the two options here for display equation on chart and display R squared on chart, and pull that up and maybe get it so I can bold it so you can see it a little better. And I could zoom in a little on that, but I think you can see it. I'm going to be typing it here in a second anyway. So you found the regression equation to be y equals 0.8303x minus 0.9467. R squared is 0.9255. R squared, closely related to this, is called the coefficient of determination. And it measures the percent of variation of pounds, in this case, the y value, as compared or explained by the percent of variation of the x values. So the closer that is to 1 or 100%, generally speaking, the better my model is. So this model is explaining just under 93% of the variation of the pounds lost based on the weeks. Now, the point of finding a model is to actually do a prediction. And generally speaking, you want to do predictions within the range of your data, but sometimes that's not useful. In this case, I might want to do a prediction for, I'll say, week 11. So for week 11, I'm going to type in 11 here, and right next to it, I'm going to go equals, because I'm doing a formula, and I'm going to go 0.8303 times, I'm going to click on 11, that's going to substitute 11 in for me, minus 0.9467. Now I'm doing this in Excel, but you could just as easily do that on your calculator. And I'm seeing that week 11, if this trend continues, I will have lost, or someone will have lost, a total of almost 2 pounds. So kind of a simple idea of what's happening here. I do want you to think about this, though. If I extrapolate too far, again, extrapolation is going beyond the range of my data. If I went out 200 weeks, would that make sense? I mean, could you sustain a diet for that long and consistently lose weight? No. So within the range of the data, this is probably pretty close, but it's not perfect. If I click back here, here's another example. This is a coolant temp sensor, and the way this one is working is it's going to have a voltage, or send a voltage to the computer in the automobile or piece of equipment. and it's going to refer to 5 volts as being minus 40, 3.45 volts being around 32 degrees, 1.1 volts being around 104, and there's more values here, but you get the idea. This is a very practical example. The voltage that's being read is not determining the temperature in the engine, of course, but it's determining what the temperature is. It isn't making a temperature, it's just giving you an indication of what it should read. So if I make a quick scatter plot here, and move this down so you can see it a little better, I can see I have a almost linear trend. There's a little bit of a curve in there, but we're going to run with it being linear. And I'm going to click plus, trend line. And again, don't worry about what I'm doing with the Excel. I'm just setting it up so I can get my trend line on there. And if I wanted the equation, I don't know why they don't make that a default, but they don't. There's my equation with R squared. So if I had a different voltage, if I went down in voltage here to say 0.6 of a volt, and I wanted to make an estimate or a prediction of what my engine temperature actually is, I would use that equation and go equals 36.61, and make sure I get my negative on there. So the equals negative 36.61 times, this time I'm just going to type the value. I'm going to type 0.6 because that's what I'm saying X is, plus 153.75. And I can see it's estimating my engine temperature 131. Okay, so that's a pretty practical example, kind of useful. And if I move this back up so I can see what I want to see here, I'm going to do some quick examples, just talking about regression again. So here I have this set of data, insert chart, and I'm moving fairly rapidly here, but I want you to see this. This data is curved. I did an example on correlation. It's not quite as bad as that one, but it is curved. And if I do the regression, I can see my R squared is down to around 0.8243. So around 82% of my variation of Y is being explained by my X. Is it okay? Or maybe it depends on the field. But that is your linear equation. Let's scroll down. Here's another one I have made up. Quickly make a scatter plot here. And I want to draw your attention to this point right there. And this is why I actually like to use Excel. This point, if you kind of turn that out in your mind, just ignore it, I'm putting the cursor over it, you can visualize a line going through those points. If I have a line going through those points, the residual, the error between the predicted value, which would be on the line, and this is rather large. This would be considered an outlier. That's what we call an outlier. And if I go and actually fit a line to it, you can see right there, put my equation in R squared because I can't help myself, move it up so you can see it. I'm seeing that, yeah, R squared is around 89%, and it should be a lot higher. Well, let's look at that data point. That data point is 2130. If I just come over to my data and delete it, and this is why I like Excel, I see that R squared shot up a little bit. I want you to notice the slope. I'm going to undo this, and I want you to look at that equation. You notice it changed a little bit, but not, move it up again, changed a little bit, but not much. Dropped. R squared went up some. Go back to here, delete that point again, watch it again. Okay, so that's what we consider an outlier. Now you have to ask yourself, well, if that's some research data, do I just throw that point out? Well, I would try and find out why it's there. Is it a mistake? Did someone write something down wrong? Experimental error? Or is it actually something happening between these data points? It could be a curve down here. You don't know. You might have to experiment more. Don't blindly throw data points out. Here's another one. Quickly do a scatter plot. Okay, now look at this data point. If that data point was not there, you could visualize a line going through those. Well, since that data point is there, let's see what happens. Okay, so my R squared is horrible. This is about 2.7% predictive power of the y's in comparison to the x's, at least the variation. That's horrible. What is occurring here is when you do regression, another name for regression is least squares regression, it is trying to shrink the distance. If I take this one here, it's trying to shrink the distance between these data points and the line. So it's always going to put the line that has the lowest sum of these square distances. Is going to do its best. This is the best because it's looking at that data point. If the line went through those, my residual would be ginormous. So this is the best fit line. But again, you might wonder what would happen if I got rid of that data point. So you'll see right there, my R squared shot up to 99.5%. My slope went positive, whereas before it was negative. Let me undo it. So right here, when I have that point left in, my slope is 0.57. When I take the point out, it's 5.7. Drastic change in slope. A lot of times it'll go from positive to negative. Huge change in R squared. This point right here is not an outlier. It's called an influential observation because it's influencing how the line is changing drastically. Another name for it is a high leverage point because it's honestly, with that data point in, this line should be going through here without that data point, but it's levering it over. So that's a quick rendition of different regression examples and why we do it, just to give you some extra examples.